Welcome to another fabulous day in Calculus 3, and we're continuing our exploration through relative extrema for functions of two variables. So, quick recap, in order to get extrema for a function of two variables, you have to first set your first partials equal to 0, solve the system, might be linear, might be nonlinear, and then the solution or solutions to that system are known as critical points. And let's say you have one of these critical points. Let's say the critical point has coordinates A, B. So then what? Okay, so you've already solved this system here. You have to do the D test, also known as the second partials test. You have to form this D quantity. And so D is a quantity that involves the second partials. So you multiply fxx with fyy, and then you subtract fxy squared. Great. So once you have that in hand, you substitute your critical point in there. And there may be more than one, so you may have to perform this test more than once. Once you evaluate D at the critical point, you have 4 possibilities that can happen. If D is positive, and these first 2 are for when D is positive, you have to check what fxx is doing. So if D is positive and fxx is also positive, evaluated at the critical point, you have a relative min. If D is positive and fxx is negative at that critical point, you have a relative maximum. If your D is less than 0, so if it's negative, you don't even care what fxx is doing. You're just like, wait, I just have a saddle point. The saddle point is neither a max or a min. We discussed this. It kind of looks like a horse's saddle. Now, if your D is exactly 0, doesn't give you any information. The test is inconclusive. There may still be a maximum and a minimum and whatever, but you might have to go to do some different things to figure it out. Okay? Test inconclusive. So let's look at some other examples here. Let's do example 3. Yeah. You know, what I'd like to do is I'd like to have you guys try this one. Let's start by doing that. How we did here. So with this guy, to find the extrema and saddle points, I hope you started off by getting your first partials. And negative 3x squared plus 4y was the fx. And I think the fy was what? Negative 4x rather. Excuse me, sorry. A negative 4y plus 4x. Okay, now you're going to set both of these equal to 0, and you're going to solve the system. Now this is a nonlinear system of equations. Nonlinear because this term right here, the negative 3x squared, is considered a nonlinear term because it's squared. The other terms are actually linear since they're only being raised to the 1 power. That's linear. But because you even have one nonlinear term in the whole thing, it makes the whole system nonlinear. So how do you solve a nonlinear system? Well, very carefully. Typically, we use the substitution method. So pick which one of these equations looks the easiest to solve for one of the variables, and it doesn't matter which one. And then go ahead and substitute it into the other equation. And now both of these equations are pretty easy to solve for, whichever, but it's kind of up to you how you want to do. I'm just going to pick this one here, and then I'm going to go, all right, I'll add 4y to both sides. Great, divide both sides by 4, and I get x equals y. Okay, now what? Well, you substitute that into the other equation. So in place of the x here, after I do this substitution, I'm going to have negative 3y squared plus 4y equals 0. Okay, now if you did it the other way where you had y equals x, don't worry, that's fine also. As long as you're doing legitimate mathematical steps, you're okay. But you have to be really careful that you do use legitimate mathematical steps, because I want to, just as a side note, show you the wrong way to do this problem starting right now, because I have seen students do this and I want to make sure I don't see this kind of mistake on a future quiz or exam, because it can be very common. And that's why I'm taking time out of the lecture to go over it, because I've seen a lot of students over the years do this, and I don't want that to be you. So I've seen students go, oh, hey, I'm going to add 3y squared to both sides. Oh, hey, I'm going to divide both sides by y. That's illegal right there. Why is dividing both sides of an equation by a variable not legal? Because the variable could be 0, and that would be illegal to divide both sides of an equation by 0. So please do not do this, and you'll end up losing information anyways. It's going to hurt you. Well, then how do you do this equation here? Well, it is a quadratic equation, so you could use the quadratic formula, although for this equation, that's a little bit overkill. The better way to do it is to factor and use the ZPP. That's the better approach. So if I factor out the greatest common factor here, I get, y negative 3y plus 4, yeah, equals 0. Great. Now I have something times something equals 0. And that's exactly where the ZPP, the zero product property, comes into play. It basically says if something times something equals 0, then you can individually set the factors equal to 0 and solve those. Now this one's already solved, and that in fact is one of our y coordinates. If we add 3y to both sides and then divide both sides by 3, we get y is equal to 4/3. Now you got to finish it up. What do we have here? We have the y coordinates only for the solutions to this system. And there are 2 solutions to the system. Okay? Yeah. Now, if y is 0, what is the x coordinate? Now remember, we did solve one of the equations and got that x is equal to y. Oh, that's easy. So in this case, it's exactly the same. Nice. Now, if you make it this far and you're on a quiz or exam, I'll give you a little bit of partial credit, because you did in fact get the correct critical points. Yay, success. But you got to finish the problem. You got to perform the D test. And remember, D is fxx times fyy minus fxy squared. So let's do this on the fly. Fxx is the derivative of fx with respect to x. So what is that going to be? I get negative 6x for fxx. And then I'm going to multiply that by fyy. Fyy is the derivative of fy with respect to y, but that's negative 4, minus fxy getting squared, which is, that's going to be the derivative of fx with respect to y. All right, I just get 4. So you're going to go 4 squared. So what is our D? Our D is 24x minus 16. There we have it. And now you can do your D test. So let's test the 0, 0 point first. So you're just going to evaluate D at the point 0, 0. I get negative 16, which is less than 0. And the theorem says we've got a saddle point. If your D is negative, you got a saddle point. So saddle point at 0, 0 is one of the answers. And then if we test the 4/3, 4/3, substitute that point into D. D only has x here, but oh, I'm going to do some reducing. 24 divided by 3 is 8. 8 times 4 is 32. Well, this is a positive number. So the theorem says if D is positive, you got to go check fxx and see if fxx is positive or negative. So when I substitute this critical point into fxx, which is negative 6x, and folks, I don't even care what the number is. A negative times a positive is obviously a negative. So I'm just going to go negative. I'm not even going to evaluate it to go get the number. Can I do that on a quiz? Yeah. Yeah, because it's obviously negative. So now what? If d is positive, but f(x) is negative, we have a relative maximum at the point 4/3, 4/3. Now, oftentimes, especially when you have maximums or minimums, they want that max or min value, which means go get the z coordinate. So the actual max value at this critical point, if you plug in 4/3 into the original function, which is kind of a pain in the butt, because it's going to be, 1 minus x cubed minus 2y squared plus 4xy. But I get kind of a weird number for our maximum. I get 59/27. And the saddle point, if you plug that into your original function, I believe you'll get a z coordinate of 1. Okay, and we're done with this example. Yeah? So this next example is an example that you can find in just about any calculus book that you buy. It's classic, and there's some that are similar to it. So you're going to try and find the extrema for fxy, 4xy minus y to the fourth minus x to the fourth. Okay? So you're going to go get fx and fy. Here we go. Let's do this quickly. So take the derivative with respect to x. I get 4y minus 4x cubed. Okay? Take the derivative again, but with respect to y. I get 4x minus 4y cubed. Set both of these partials equal to 0. This is definitely a nonlinear system. Oh, yeah. Because the x cubed and y cubed terms are nonlinear. So again, the substitution method is your best bet to solve this nonlinear system. And it doesn't matter which one of these that you decide to solve for. How about if we take this first equation and solve it for y? So add 4x cubed to both sides, divide both sides by 4, and I get that y is x cubed. So what does that mean? I'm going to substitute y equals x cubed into the other equation. Now let's be very careful here, because this is where I have seen students make really silly mistakes. Oh boy. Yeah, they forget all their algebra. And that's the shame, because then the whole problem goes down the drain. So when you substitute x cubed in here, what does this term simplify to? Does anybody know the exponent law? That
9.
Yes, the power to a power rule. Please remember, when you have a power to a power with exponents, you multiply the exponents together. So it's not x to the 6th, it's x to the 9th. So this equation here, when I clean it up a little bit, is 4x minus 4x to the 9th equals 0. Again, please don't make the mistake that I went over last time. Side note, once again, please don't do the following. Oh, let me just add 4x ninth to both sides, and then I'll divide both sides by 4x. No, 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 no. You're not allowed to divide by a variable. Please don't ever do that. What do? Factor and do the ZPP. That's going to be your friend. Factor and use the ZPP. So I'm going to factor out the greatest common factor here. Which is a 4x. Okay, fine. And then I'm going to get 1 minus x to the 8th. Yeah. And that's equal to 0. And now the ZPP says if something multiplied with something else equals 0, you can set each individual factor equal to 0. That's the ZPP. Now, this 4x equals 0, if you divide both sides by 4, you get x equals 0. And that is going to be one of the x coordinates for a critical point. And then this is kind of scary. That's an 8th degree polynomial equation. When you took pre-calc and you learned the fundamental theorem of algebra, I hope you remember that a polynomial equation of 8th degree would have 8 solutions, but some of them might be real, some of them might be complex. And in this class, we ignore any complex number solutions, okay? This class, for those of you that are taking differential equations or you plan to take differential equations, please, please know that this has 8 solutions total. Because they'll get you in differential equations. They do care about complex numbers in that class. Differential equations is God's gift to electrical engineers. Yes, if you're an electrical engineering major, take your differential equations class. Yeah, work hard. Electricity requires complex numbers in order to deal with it, okay? So we're not going to get 8 solutions. Here's what we are going to get. You'll see. I only care about real numbers. So you're going to add x to the 8th to both sides. And you're going to take the 8th root of both sides. But does anybody remember what you have to do when you take an even root of both sides of an equation? Like square roots of both sides? What do you have to remember?
Absolute value.
No.
Plus or minus.
Plus or minus. Thank you. Aha. X is plus or minus 1. So of the 8 solutions to that 8th degree polynomial equation, 2 of the solutions are real. The other 6 are complex numbers, but we don't care about those. We want the reals. So folks, I claim we're going to have 3 critical points total. Oh my goodness, it's getting kind of complicated. Yes, indeed. One of the critical points has an x coordinate of 0, one with 1, one with -1. By the way, this plus or minus is very important to me, and it's one of my pet peeves. So I'm giving you a little hint. It's somewhere on your quizzes and your exams and the final. I'm going to make darn sure that you get that when you take an even root of both sides that you're solving an equation for, plus or minus. Plus or minus. Yeah. Moving on, how do we get the corresponding y coordinates to these 3 critical points? Well, shoot. Remember they said that y was equal to x cubed when we were solving one of the equations for x? Let's use that. So if y is equal to 0 cubed, we'll get 0 for the y coordinate. Okay. If y is equal to 1 cubed, we'll get 1. -1 cubed is -1. Oh, wow. Okay, fine. So now it's time for the D test. So let's go get D. D is fxx times fyy minus fxy squared. Here we go. Fxx, if we look at fx and take the derivative of fx with respect to x, I get -12x squared. Fyy, the derivative of fy with respect to y, -12y squared minus fxy getting squared. So fxy is when you take the derivative of fx with respect to y. I get 4. So if I clean my d up, this is a negative times a negative. That's positive 144x squared y squared minus 16. Okay, we have to perform the d test 3 times. That's right. Once for each of these 3 critical points. Here we go. So let's test 0, 0. D evaluated at 0, 0. It's going to give me 0 minus 16, which is negative. Guess what? I get a saddle point at 0, 0. Great. And you can go ahead and get the z coordinate. I got it. It's also 0. Let's test the 1, 1. So when you evaluate D at 1, 1, I get 144 minus 16. I don't even care what the number is, people. I really don't. It's obvious it's positive. And then fxx evaluated at 1, 1 is a negative number. So that tells me I have a relative max at the point 1, 1. And if you plug 1, 1 into your original function, that's this guy here, 4xy minus y to the fourth minus x to the fourth, you'll get the z coordinate. That's the actual max value. The maximum is a 2. If you test -1, -1, your d is still going to end up being a positive number. -1 squared is positive. And your fxx evaluated at -1, -1 is negative again. So you have another relative max. Can you have more than one? Oh yeah. There's no limit on how many extrema you can have, and maximums or minimums. So your relative max, your other one, is located at -1, -1. Also has a z coordinate of 2. That doesn't always happen, but it could. So we have 3 items of interest. 3 key items of interest for this problem. We had a saddle point and 2 relative maximums. And that concludes that example. Yes, to find the z coordinate, you need to substitute the critical point into the original fxy equation. True. Okay, boy, I wrote all over this one for problem here. Example 6. This one is different from all the problems we've done so far. And that's why I put it here, because I want you to be able to see a little bit of everything. How is it different? Well, so far, all the problems that we worked on, the function we were trying to figure out had any extrema or saddle points was a polynomial function. And those are fun. But those aren't the only type of functions out there in the world, you know. There are exponentials. So we're going to look at an exponential. But before we do, let's have a little fun. I want to see what that equation looked like from the one we just finished, the one that was 4xy minus y to the fourth. Minus x to the fourth. Let's see what it looked like. Whoa, that's great. So I hope you can see that it has 2 maximums and the saddle point located right there at the origin there. That looks like a saddle there. Pretty cool looking surface, huh? Exciting. Rainbow, yay. Fun. Let's look at the graph of this exponential we're about to do. Let's see if it will graph it for me. Oh my gosh. E to the x squared minus y squared. Oh my goodness. Minus 2x minus 6y minus 3. Get all that? All right. What does it look like? Whoa. Well, that's kind of cool, huh? Cool looking surface. So we're going to see if this has any maximums, minimums, or saddle points in it. I don't know. We'll find out. So this one's a little bit trickier, and it requires all of our resources from calculus and pre-calc and all that stuff. So let's take a look at this guy. So first, get your partials. All right. So I'm going to do this a little bit loosey-goosey here, but to take a derivative of e to the something, e to the u, from Calc 1, you learned using the chain rule, it's e to the u times u prime, where this u prime would be the derivative of that u with respect to x. So it's going to be e to the, I don't even want to write it all out, e to the blah, 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 times the derivative of the blah, 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 with respect to x. Well, that's just going to be the quantity 2x minus 2. So the partial with respect to x is 2x minus 2 multiplied by e to that whole thing. Similarly, the fy is e to the blah, blah, blah. And then when you take the derivative of that big exponent with respect to y, I get negative 2y minus 6. Okay, you're going to set both of these partials equal to 0 and solve the very nonlinear system of equations. Now, let's think this through, okay? Folks, when you have a product equal to 0, it's got to be true that one or the other of the factors or both are equal to 0. However, you have to know a handy fact that you learned from pre-calc. E to the something is always positive. It's just positive. So it will never be equal to 0, ever, not in a million years. Since that's the case, we can basically say, well, then 2x minus 2 equals 0. And then for the other partial, the negative 2y minus 6 equals 0. And when we solve for x and y for these two little equations, I get that x is 1 and y is negative 3. So it turns out we've got a critical point, folks, and it's just one critical point. Okay, fine. Now the hard part. How do you get D? Because, you know, you got to get the fxx and the fyy and the fxy. So I'm going to be a little cavalier here. So let's get these second partials and then we'll put it all together. Fxx is going to require the product rule. Well, how come? Well, because you've got the 2x minus 2 multiplied by the exponential, and both of those factors have an x in it. So let's do f prime g plus g prime f. So if you take the derivative of 2x minus 2 with respect to x, you'll get 2. And then multiply that by the exponential, okay, e to the blah, 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 plus, and now the derivative of e to the blah, blah, blah with respect to x, and we already know what that is. It's 2x minus 2 times e to the blah, 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 times the 2x minus 2. So now we have 2x minus 2 squared. So there's fxx. Fyy, you're also going to need the product rule. So you're going to go, okay, what's the derivative of negative 2y minus 6 with respect to y? Negative 2. And then multiply that by the exponential, plus the derivative of the exponential, and again, that's the e to the u prime, times the negative 2y minus 6 again. So that just means we have two factors of negative 2y minus 6. I put the squared, okay? What about fxy? Well, good news, we do not need the product rule. So you're taking the derivative of fx up here with respect to y. So the 2x minus 2 is just a constant multiple, and then multiply that by the derivative of the exponential with respect to y. But that's going to be e to the blah, blah, blah times the negative 2y minus 6, okay? Hold your fire. So your D is going to be the fxx times the fyy minus this fxy getting squared. XY. Let's think this through slowly here. If you put, or substitute rather, this one singular critical point into the D, let's think, watch. When you put it into fxx, the 2 times 1 right here minus 2, this term will go to 0. So he's gone. So you're only going to have the 2 to the e to the blah, blah, blah. So you're going to have, you know, 2 e to the whatever it is when you substitute the 1 negative 3. I don't feel like doing it. Okay. Times your fyy when you plug the 1 negative 3 into him. This term, when you plug y equals negative 3 in there, that term goes to 0. So you're only going to have the negative 2 e to the blah, blah, blah. And then minus your fxy getting squared. But if you look at your fxy, when you plug in x equals 1 and y equals negative 3, your fxy evaluated at this critical point is going to be one big fat 0. So he's gone. So all you have here is negative 4 e to the blah, blah, blah. But that's always going to be a negative number. So we have a saddle point at this point, 1 negative 3. Now, does that always happen for exponentials? No, you can have an exponential that has a max or a min. This particular one ended up having a saddle point, which is kind of, see that. Yeah, let's keep going for the second partials test to fail here in the next problem. Fxx is 2xy squared. Fy is 2x squared y. Set these both equal to 0. You have a nonlinear system. Now, this one's weird because it's obvious that 0, 0 is a critical point, right? So obviously, the 0.00 is going to make both of those equations go to 0. I mean, if you use the ZPP here, you'll go, okay, well, 2x equals 0 or y squared equals 0, or they both do. Okay, fine. But I want you to notice there's actually infinity critical points. Wait, what? Not just 0, 0? For this problem, yeah. So take a look here. If you let x equal 0, just look at that alone. Like, don't even bother doing that yet. When you plug x equals 0 into the other equation, it goes to 0 also. I don't even care what y is. Let's pretend y is 10, not 0. Like, let y be 10 right now and just the x be 0. Do you see that both equations, when you plug in x equals 0, y equals 10, it does satisfy that? They both will be 0. So what I'm saying is this, in this line, x equals 0, and you can graph the line x equals 0. That's a vertical line that lives on top of the y-axis. Here's a graph of x equals 0. And this line has infinity points on it. So that's those are critical points. And then further, if you look at the other equation, if you let y equal 0, and then I don't care what x is, like let x be 5. If you plug in the 0.50 to either of those partials, they'll go to 0. So I claim y equals 0, which is a line that lives on top of the x-axis. All of the points on that line satisfy that system. So we have infinity critical points. That's crazy. Are we going to have to do the d-test infinity times? No, we're not. But, you know, we could. No, we're not going to do that. Don't worry. So what now? Well, if you go get fxx, let's get the d. Let's put the d together. Let's go get those second partials. So fxx is 2y squared. Fyy is 2x squared. And then fxy is what? 4xy. All right. And then you're going to square it. Ooh, cool. So what do I have here? I have 4x squared y squared minus 16x squared y squared. Oops. So it looks like d is equal to negative 12x squared y squared. Okay, fine. So now if you plugged in, say, 0, 10, d is 0. If you plug in 10, 0, d is 0. So this means test inconclusive for any of those infinity critical points. So are they maxes, mins, or what? Let's look at the graph and then you'll see. I hope you can see that x squared y squared is always going to be non-negative. So it's either going to be 0 or something positive. So what's the lowest it can go? Well, 0. So that gives you a little insight into what these infinity critical points might be yielding. Maybe, maybe not. Check it out. Can you see that you have rain gutters along the x and y axes? I don't know if you could see that. I claim you have infinity relative minimums. Kind of hard to tell. So maybe what I can do is I'm going to try to draw this a little bit, just a portion of it. So here in 3D, along the x-axis, you have sort of a rain gutter happening there. And then the same thing along the y-axis. You guys know what I mean by rain gutters? Like that. So you've got infinity minimums along those rain gutters. And that's kind of what this surface is, if you can kind of see what's going on there. You have those minimums all along the x and y axes. Kind of cool. Love that problem. Okay. So how about you guys do example 8 right now? I'm going to put you in your breakout rooms. Let's just try that now. Let me add a couple more rooms. Okay. Let me open the rooms. Go ahead in your rooms, and I'm going to assign Kelvin, Aaron, and Roman to room 8. So you guys go to room 8, okay? There you go. You're all set. Enjoy. Woohoo! So that was just an easy problem that I took from a business calculus test. Yeah, business calculus does relative extrema in 3D. So if they can do it, so can you. So all you had to do, I mean, they didn't give you the original function, but you didn't need it. They told you there was a critical point at this point, x naught, y naught. We don't even know what their coordinates are, but they did give you the second partial. So if you put it together and you went, okay, fxx times fyy minus fxy getting squared, I get 24 minus 4. I don't even care what the number is. It's positive. So now what? Well, the theorem says if D is positive, you got to go check what fxx is doing. But it looks like fxx is -3, so that's negative. So if D is positive, but fxx is negative, you got a rel max. And that was the answer. That's all you had to do. Easy peasy. Okay, and now I'm going to do the grand finale problem for this section, and then I'm going to do the 2-word problems for this section. Okay, and that'll complete today's lecture. Okay, I know. So, example 9. Now, I'm going to say something about example 9. It is going to be similar to a quiz question on this weekend's quiz. So please pay attention. It's a little bit trickier than most. So try to follow why it's a little bit different flavor than what we've been doing so far this whole section. Okay, it's not totally different, but the ZPP is going to save the day. I'll tell you that. So you know, go get fx and fy. So let me just copy down fxy here. We've got y cubed minus 3x squared y minus 3y squared minus 3x squared plus 1. Okay, so that's our original function. Figure out if there's any extrema or saddle points going on for that function. Fine. So I'm going to go get my first partial. So fx, all right, what do I have here? -6xy, and then a minus 6x. I think that's it. When I get the other partial with respect to y, definitely got the 3y squared there from the first term, minus 3x squared from the second term, and then minus 6y from the third term. And I think that's it. Oh, okay. Set both of these equal to 0. Oh my God, that is a serious nonlinear system of equations. Oh dear God. Okay. This is where it gets a little weird, okay? You got to be careful because you don't want to do any moves that would be considered illegal mathematically. For example, please don't ever divide both sides of an equation by a variable. It's just going to just destroy all your chances to maximize your points, okay? So we're going to use the substitution method, of course, but it's going to be very interesting what happens here. So watch closely. I'm going to take the very first equation that involves fx, and I'm going to factor out a common factor. And it looks like -6x is common to both terms, all righty. And then that means the other factor would be y plus 1, and that's still all equal to 0. And now the ZPP, the zero product principle, or zero product property. If something times something is equal to 0, that's exactly what's going on here, then you set each of the factors separately equal to 0. Now, this is where it gets a little tricky. If you solve the first equation for x by simply dividing both sides by -6, okay, you'll get x equals 0. Fine. But here's the big mistake students make. They go, oh, I'm going to solve the other equation for y, And oh, doesn't this mean that 0, -1 is a critical point? No, not a critical point. Why not? It looks like it would be. Okay, let me argue why not. Because this point would only make fx equal to 0. You can even try, plug it into fy, and I tell you that it will, it's not going to make fy equal to 0. I challenge you to go plug it in to the fy. Go do it right now, like on the side margin. Your fy is not going to be equal to 0, okay? It's going to equal some other number that's non-zero. So don't do that. Well, now what? I'm trying to make this not mysterious. Try to follow this. Well, it's late and I'm tired. Long lecture. Yeah, I get it. You're gonna separately plug these into fy to get the corresponding other coordinates. So substitute x equals 0 first. Okay. So in other words, fy evaluated when x is equal to 0 would be 3y squared minus 3x squared, but we're substituting x equals 0 minus 6y equals 0. Now what? Well, I get 3y squared minus 6y equals 0. Now what? Factor and use the ZPP again. Oh, are you serious? Yes. I'll factor out a common factor of 3y, and then the other factor is y minus 2, and then I apply ZPP again. So 3y times y minus 2 is equal to 0. I got 3y equals 0, or y minus 2 equals 0, or maybe they both do. Divide both sides by 3 for that first guy, I get y equals 0. Add 2 to the other guy, I get y equals 2. What does this mean? It means that when x equals 0, those two things can happen. So we have two critical points right now. Two of them, 0, 0, and 0, 2. But we're not done. Let's save these for later. I'm going to put those on the back burner. Really? We got more happening? Oh, yeah. This problem is intense, baby. I'm not making this up. Oh, you're putting one of these on the quiz? Yeah. Okay, you're going to take the other value we got, y equals 1, and you're going to substitute this into fy. Really? Do a little partition here because this is getting quite messy. So where was my fy? He was up here. Okay, so if we substitute y equals -1 into this equation, we also want the equal 0 part. We will have what? 3 times -1 squared minus 3x squared minus 6 times -1 equals 0. Solve this equation for x. Okay. I get 3 minus 3x squared minus the minus is a plus 6. I get 9 minus 3x squared equals 0. I add 3x squared to both sides. Okay, I get 9 equals 3x squared. Let's divide both sides by 3 next. Okay, and then I get x squared equals 3. Now you're going to square root both sides. But what do you have to remember when you square root both sides, people?
A plus or minus.
Yes. Thank you. La, 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 la. And so I get two answers here. Oh man, what does that mean? What it means is you have two more critical points when y is -1. Remember, we got all this from substituting y equals -1 into the situation there. So you could get square root of 3 -1 or the negative square root of 3 -1. So now we have 4 critical points in all. Is that possible? Yes, it is. So what? I think I skipped the problem. I think I skipped example 4. I'll come back and get it. Yeah, we're going to go late today. Sorry. I have to talk about something else. 4 critical points total. Now what? Well, you got to do the D test 4 times. Are you serious? Yes. I am completely serious. Like, would I lie about something like that? No, I would not. Well, you know, I'm getting tired. Well, grab a coffee or a tea or a Monster. Keep going. All right. So you're going to need to perform the D test 4 times. Oh boy. So what is D? All right. Well, here we go. D is fxx, which is going to be what? And I'm going to do this kind of quick here. I got negative 6y minus 6. And then you're going to multiply that by fyy, which I get 6y minus 6. Wow, that's interesting. And then minus fxy squared. So I get 6x squared. Okay. So there's your D. So I'm just going to cut to the chase. Here's the deal. Because I know we're running a little short on time and I still want to do word problems. So what happens when you evaluate D at the point 0, 0? You will get, let's see, negative 6 minus 0. You'll get something. You'll get something negative, I believe. Is that right? It's one of our 0, 0. Yeah. So you're going to evaluate this and you'll get, oh no, wait, sorry, you'll get something positive. What will you get? You'll get
36.
Yeah. You should get 36. You're gonna get 36, is that right? Yeah, and that's positive. So then you're gonna go, what's fxx evaluated at 0, 0? And you're gonna go, well, negative 6 times 0 minus 6, that's a negative 6, that's negative. So you get a real max at the point when x and y are 0, 0. And if you go get the actual max value, it's a 1. Okay, so you got that. And then if you go D evaluated at 0, 2, what happens? So when you plug 0, 2 into this situation, you're going to get what? Negative 6, negative 6 minus 0 again. In a second here, I'm doing something. Always happens when I try to hit it too hard. So you're going to have, this is what, negative 18 times 12 minus 6. So that's going to be something positive 6. This looks like it's going to be negative. So now what? Saddle point. Because we got a negative D. And it turns out that the other points also give, you're going to end up with a negative D also for both of those other saddle points. You can check me out if you don't believe me. So you're going to have 2 more saddle points. Can you have 3 saddle points total? Sure. Why not? So your overall answer is you have 1 relative maximum and 3 saddle points. Oh my goodness, that's nuts. And so the real max occurs at the 0, 0, 1, and your 3 saddle points occur at 0, 2, negative 3, and then plus or minus square root of 3, negative 1. They those two guys have the same z coordinate. So that's pretty crazy. That's a pretty crazy problem. So let's recap. Why was this a little bit weird? Because you got into a situation where when you were getting your fx and you were applying the ZPP right here, you got an x and a y, but it was not correct to put those two together and call it a critical point. You had to individually take one and then the other and substitute into the other partial to get the critical points. And it turned out there were 4 critical points in all. That's nuts, right? And then you had to do the D test 4 times, which is extreme nuts. So I think I forgot to do example 4 because I never leave myself enough room. And I want to talk about that because that particular example, which is also classic, is what I call sort of a non-genuine system of equations. So what do I mean? So I skipped it way. Yeah, sorry, not too far. So we forgot to do this guy. Let's do this now. So if I do example 4, I got fx. Well, that's 4x cubed minus 32. Fine. Fy. That's 5y to the 4th minus 5. Set both of those equal to 0 simultaneously. So I want you to look at this system here. It is nonlinear, that's for sure. Yeah, it's got nonlinear terms in it. However, do you notice how the fx doesn't have x's and y's in it? It just has one variable, x only, and the fy just has y. So if you get a system where each equation has a single variable in it only, it's not considered a real system of equations. And it actually is kind of easy to solve, but you have to be careful if this is the case. Here's why. For the first guy, solve it for x. So if you add 32 to both sides, you get 4x cubed equals 32. And then if you divide both sides by 4, you get x cubed equals 8. And then if you cube root both sides, and no, you don't need a plus or minus when you cube root both sides, okay? That's only for taking an even root of both sides. I get x equals 2. So save that. When you solve the other equation for y, add 5 to both sides, divide both sides by 5, and now you're going to take a 4th root of both sides. Yes, you need a plus or minus, because anytime you take an even root of both sides, you got to do the plus or minus. And now what you have to do is you have to do what I call mixing and matching when you have these not genuine linear systems of equations. So you're going to get 2 critical points, 2, 1, and 2, -1. Okay, so you have 2 critical points here, and that means, okay, we'll go do the d-test on them. And the d-test is pretty easy on this one. It's just a polynomial function, so these are really easy to get. So your d is going to end up being fxx, which is 12x squared, times fyy, which is 20y cubed, minus fxy squared, which is 0. And if you evaluate either of these, well, let's do the 2, 1. And I'm not even going to plug this in. I mean, this is like, okay, yeah, 12, blah, blah, blah. You're going to get something positive. I hope that's obvious because you've got a squared there. That's 1 cubed. It's positive. So now what's fxx evaluated at 2, 1? Well, it's going to be positive also. Okay, fine. So when both d and fxx are positive, you have a relative min.
Is this supposed to be -1 for the second one?
Yeah, we're going to do the second one in a minute.
Okay.
Right now, we're just testing 2, 1. And it's a real min. Now let's test 2, -1. Is that okay if I do them separately?
I thought you were doing the 2, -1 with for the fxx. That's why I got confused.
No, I'm doing a 2, 1 for both. Okay, and now let's test the other guy. When you plug in the 2, -1, you're going to get a negative number. Why? This is positive, right? And 20 is positive, but -1 cubed is negative. So positive times a positive times a negative is negative. So I don't even care what the number is. I don't even whip out my calculator and waste valuable time. It's negative, saddle point. So for this problem, we have a real min at the point 2, 1, -60. And we have a saddle point, and I plug in these values into the original problem, 2, -1, and I think the z coordinate is -52. Okay, and that's the final answer for that. So why did I want to put that one in my lecture? Because I think it's important for you to see a problem where you don't have a system of equations that's got x's and y's in both equations. Okay, so because sometimes that happens. All right, that concludes that example.